Polar coordinates. Polar coordinates gives us an alternative method for locating points in the plane. So if we have some point here called the pole, and we have a ray coming from that point going to the right, which we call the polar axis, we can locate a point P by simply looking at the distance that this point is from the original point here and the angle through which we have to rotate to get to that point. And so polar coordinates give us two coordinates, r and theta, where r is this distance from the pole to the point, and theta is the angle that we have to rotate through to get there. Now, just a couple of details about this. The angle theta is not unique because, as you know, if you rotate to some spot here, you can add 2 pi to that, and you will still be at that same location. You can also subtract 2 pi, and that will put you back at that same angle as well. So when we give coordinates in polar form for a point, these coordinates are not unique. Also, this value r is the distance, but it's not always going to be a positive number. So for example, we do allow for r to be negative, and in the case where r is negative and you have some angle theta, you would rotate through that angle theta, and then if r is negative, you go in the opposite direction from that angle theta. So that means instead of your point being located here, a distance of r units from the pole, it's located 180 degrees from there. But the distance is still r, so to speak, but it's actually the absolute value of r, because if r is negative, then we need to make it positive before we can talk about it as a distance. Let's take a look at some examples. So here we have several points in polar coordinates that we want to graph. The first point is the point 1, 3 pi over 4. Now, when graphing a point in polar coordinates, the first thing you actually want to do is go to the angle. So starting from our polar axis, the angle 3 pi over 4 is over in this direction. And then the 1 just tells us the distance from this point out to this point. So this is where that point would be located. The next point, 3 negative pi over 6. Again, starting from the polar axis, we rotate negative pi over 6. So that's in the clockwise direction. And then we're going out 3 units from there. And you can see the 3 marks here to indicate that this is 3 units. Next, we have the point 3 pi. The angle 3 pi starts from the polar axis and rotates 1 complete rotation, takes us to 2 pi. And then 1 more half rotation takes us to the angle 3 pi. And then from there, we go a distance of 3 units. And finally, we have negative 4 pi over 4. So again, from the polar axis, we rotate pi over 4. That puts us at this angle. But because r is negative, we're actually going to travel in the opposite direction 4 units. And that's where this point would be located. Polar coordinates are not unique for a given point. So this example shows you how you can have different polar coordinates for the same point. So first, we'll just graph the point with polar coordinates 2 pi over 3, and then we'll find some other representations of that same point. So if you just look at all these graphs, notice that the point in all these graphs is in the same location, but all the coordinates are different. So first of all, to graph the point 2 pi over 3, we're going to rotate an angle pi over 3 and then go out 2 units from the pole. So that's where this point would be located. Now, 7 pi over 3 would locate the same point, and the way we get 7 pi over 3 is simply take pi over 3 and add 2 pi to it. So pi over 3 plus 2 pi is 7 pi over 3. In the next one, we have the point 2 negative 5 pi over 3. And to get negative 5 pi over 3, we're simply taking the original angle, which is pi over 3, and subtracting 2 pi from it, and that gives us negative 5 pi over 3. Another option is, rather than rotating to this angle, we can rotate to the angle that is 180 degrees from that angle. So if we have an angle of pi over 3 here, the angle down here is 4 pi over 3. And we get this angle by simply taking pi over 3 and adding pi to it. That's 4 pi over 3. So if we have an angle of 4 pi over 3, that puts us down here in this direction. But then if r is negative 2, that throws us back in the opposite direction, which puts us back up at this point. And finally, negative 2 pi over 3, the way we can do that is by simply subtracting pi from the angle, right? So again, we want to start down here at this angle. To start there, we're just going to take pi over 3, and we're going to subtract pi, which gives us negative 2 pi over 3. And that puts us down here, but then again, if r is negative 2, that flips us back in the opposite direction. So all of these polar coordinates locate the exact same point in the plane. Next, and perhaps most important, we want to look at the relationship between polar and rectangular coordinates. So the rectangular coordinate simply refers to when you have an x-axis and a y-axis, and you locate a point by simply giving the coordinates x and y. So what is the relationship between polar coordinates and rectangular coordinates? Well, if we have a point located in the plane here, we know the rectangular coordinates can be given as x and y, and by the way, those are unique. And then the polar coordinates can be given by locating the angle theta and the value r that gives you that same point. And when you put all these together, you can see that you get a right triangle here. Now, this right triangle has relationships using trigonometry. We know that cosine of theta is x divided by r. We know that sine of theta is y divided by r. So if you solve for x and y, you get x equals r cosine theta and y equals r sine theta. And that's where these equations come from. Also, we know that x squared plus y squared must be equal to r squared. And we know that tangent of theta must be equal to y over x. So we have these 4 equations that help describe the relationship between x, y, r, and theta. So as an example, we can convert polar coordinates into rectangular coordinates. So if I have the polar coordinates 4, 2 pi over 3, let's just note that this means r equals 4 and theta equals 2 pi over 3. We can convert this into rectangular coordinates by simply using the formulas on the previous page. So I can find x and y by applying these 2 formulas. And this is going to give us x equals 4 cosine of 2 pi over 3 and y equals 4 sine of 2 pi over 3. And then we just plug in the values. So the cosine of 2 pi over 3 is negative 1/2. And so this gives us a value of negative 2. And the sine of 2 pi over 3 is radical 3 over 2, which gives us 2 radical 3. So in rectangular coordinates, this is going to be negative 2 and 2 radical 3. And then what you can do is you can graph these together to show that they represent the same point. And so to do this, let's just recall that radical 3 is about 1.7, so 2 times radical 3 is about 3.4. So we can approximate this by graphing the point negative 2, 3.4. And that is going to be right about here. And then notice that if you draw a line segment to the origin here, this angle right here would be 2 pi over 3, and this would be 4 units. And if I show the triangle here, this is the negative 2, and this is the 2 radical 3. And you should recognize that this is a 30, 60, 90 triangle there. We can also convert from rectangular coordinates into polar coordinates. Now keep in mind, when you convert into polar coordinates, there is no unique answer. However, the answer that we typically give, if we just want to give one answer, is we want to have r be a positive number, and we would like for our theta to be between 0 and 2 pi. So to find the polar coordinates for the point that has rectangular coordinates 2, -2, notice that we can graph the point 2, -2, which is right here. That's simply x equals 2, y equals -2. And then that creates a triangle. And we should know that this angle right here is 45 degrees. And that's because the x and y coordinates are equal in terms of their length. And since that's the case, then we know the hypotenuse here must be 2 radical 2. This is just knowing the 45, 45, 90 triangle. Now, of course, you can use the formulas x squared plus y squared is equal to r squared. And then you can just plug these values in. And so this gives us 8 equals r squared, or r equals the square root of 8, which is 2 radical 2. So that's another way that we could figure out what r is. And then the angle, of course, the angle is just the angle from here to here. And so that angle, again, we could choose lots of different angles. But if this is 45 degrees, this angle would be 315 degrees, or 7 pi over 4. And so one way to give the polar coordinates for this point would be 2 radical 2, 7 pi over 4. And again, there are many correct answers for this, but this is the typical answer that they would give. Now, if you look at the answers that they provided here, they gave 2 radical 2, and then they just expressed this angle as a negative angle, so negative pi over 4. And then they also gave an answer where r was -2 radical 2, but then the angle has to be 3 pi over 4, so that when the r is negative, it takes you in the direction that you want to end up in. So again, all of these are correct answers, but this is the one that I would typically give. We can also convert an equation from rectangular to polar coordinates. So for example, x squared is equal to 4y. We can write this in terms of r and theta by just knowing our conversion formulas. And so if you keep in mind these formulas, notice that we can replace x here with r cosine of theta. And we can replace y with r sine of theta. And if we do that, we have r cosine of theta, quantity squared, is equal to 4 times r sine of theta. And this is r squared cosine squared theta is equal to 4r sine of theta. And what we typically like to do when we're putting an equation in polar coordinates is we like to solve for r if possible. So what I'm going to do here is I'm going to divide both sides by r cosine squared of theta. What this will do is it will cancel one of these r's here, and then the cosines will cancel there. And we have r is equal to, on the other side, the r's cancel out, and we have 4 sine of theta over cosine squared of theta. And this can be rewritten as 4 sine of theta times secant squared of theta. And if you don't like this particular format, another way you could give this answer is you could take this and rewrite it as 4 sine of theta over cosine of theta times 1 over cosine of theta. And this would give us 4 times tangent of theta times secant of theta, which we typically write as secant theta tangent theta. So both of these are equivalent, and either one would suffice. Now we can also convert equations from polar to rectangular coordinates, and it pretty much works the same way. So we're going to take our conversion formulas, And then we're just going to play around with the equation that we're given to see how we could apply these conversion formulas to these equations. So in part A here, we have r equals 5 times secant of theta. We can rewrite this as r equals 5 over cosine of theta. And then if we multiply both sides by cosine, you can see that we get r cosine of theta equals 5. Well, r cosine of theta is x, so this can be converted into x equals 5. And of course, we could graph this. This would just be a vertical line at x equals 5. I'll leave the graphing as an exercise. In part B, we have r equals 2 times the sine of theta. And in this case, it's a little bit less intuitive, but if I multiply both sides by r, so we have r times r equals r times 2 sine of theta, this is going to give us r squared equals 2r sine of theta. And then we can replace r squared with x squared plus y squared, and we can replace r sine of theta with y. And so this becomes x squared plus y squared is equal to 2y. Now you could leave the equation like this, but you could also do a little reorganizing here. So if I subtract 2y from both sides, this will be equal to 0. And then if I complete the square here, that would involve just adding 1 to both sides. And then if we refactor this, you can see that we get this equation. And this, of course, is the equation of a circle. The center of that circle would be at the point 0, 1, and the radius would be 1. And so this circle would look like this. And finally, in part C, we have r equals 2 plus 2 cosine of theta. And this one is perhaps the least intuitive. But once again, what I'm going to do is multiply both sides by r. So that's going to give us r squared equals 2r plus 2r cosine of theta. And then we know that r squared is x squared plus y squared equals 2r. I'm going to leave as is for the moment. And then we have plus 2 times r cosine of theta, which is x. Now what I can do is subtract 2x from both sides. So right now we're kind of in limbo, right? Because we have x's and y's and we have r's. And of course, we're trying to just get x's and y's. So we're, kind of in the middle of the process here. But now what I can do is I can square both sides. And when I square both sides, we get x squared plus y squared minus 2x, quantity squared, equals 4r squared. And then r squared, of course, is x squared plus y squared once again. So we get 4 times x squared plus y squared. And I wouldn't even attempt to try to graph this because this equation is extraordinarily complicated. And this is perhaps a great place to end because one of the reasons we like polar coordinates is that for some situations in rectangular coordinates, it would be extraordinarily complicated. However, in polar coordinates, notice the equation is much simpler and also easier to graph. And that concludes this video lesson.